Hey, it's Dave here. In this video, I'm wrapping up my IR and RF Hub series, a project that lets you clone remotes and use Home Assistant to control things like TVs and motorized curtains. If you haven't seen the previous parts, I'd recommend you watch those first, link in the description. In this video, I'm covering the hardware side, the carrier PCB, why I designed it this way, how to assemble it, then cover the 3D printed enclosure, explain the design choices, and show you how to print and fit all the pieces. Now, regarding this infrared and RF hub, just a quick note, my RF testing focused on the 433 MHz frequency. When I designed this carrier PCB to work with RF modules, I encountered two different variants, a green one and a blue one, each with different pinouts. Instead of just supporting one, I designed it with two separate footprints, one for each variant, so you can choose whichever module you have, the green one on one side and the blue one on the other. Later, when I assembled it, I found the blue variant was experiencing some noise, but that has been resolved after adding a ground copper pore onto the PCB design. The description has a link to the latest version with all those improvements. This board was made possible by PCBWay, who sponsored this series. PCBWay offer PCB manufacturing, 3D printed and CNC services. They have a community project share section where you can upload and share your designs and others can order them directly. I've uploaded this IR and RF hub to their community share. If you want to build one, use the link in the description to place your order. And this month, PCBWay's celebrating their 12th anniversary with 3 solder mask colors, matte black, purple or pink on rigid, flexible and rigid flex PCBs. Orders must be placed and reviewed by July the 31st to qualify. Check the link in the description for more details and exclusive coupons. Now, looking at the PCB design itself, I purposely structured it so some components are soldered directly onto the board while others connect via female header pins. I did this intentionally so the more expensive bits can be removed and swapped out if they fail, so you don't have to replace the entire PCB and resolder everything from scratch. The components that connect via the female headers are the ESP32 dev board, the RF modules, the light sensor, the temperature sensor, and a breakout board if you want to add extra components yourself. The IR LED transmitters and receiver are soldered directly onto the board, but at a specific height. To ensure their position consistently at the right elevation, I designed a 3D printed guide, one for the transmitters and one for the receiver. You can use these during the assembly to align everything perfectly before soldering. Now, because I'm using a development board alongside all these components, one challenge is it has a built-in power LED always on whether you want it or not. Since I'm using a light sensor, the LED light interferes with the readings. There's a few ways to solve this. You can cover the LED with black electrical tape or desolder it entirely if you're confident in doing so without damaging the board. Instead, I decided to design a solution into the 3D printed enclosure by adding a shield, basically a small wall that blocks most of that light from reaching the sensor. That way, the light sensor reads accurately without any modifications to the board itself. The enclosure design exposes the key components where they need to work. The 4 IR transmitter LEDs pop through the holes in the corners for a 360-degree coverage. On the left, there's an opening for the light sensor so it can read ambient light without interference from the board's power on LED. And in the center, the IR sits in its own recessed area with a clear opening so it can receive signals from your remotes. For the 3D printed enclosure, you need the 4 parts. The guides, one for the IR transmitter, one for the receiver, which helps you solder them at the correct height as mentioned earlier. The base is where the PCB sits, and the cover you have two options, the standard one or an alternative if you're using the breakout headers for extra components. The base and the lid needs to be orientated as shown in the slicer. I printed everything in black PLA intentionally. Black plastic blocks the onboard LED light from shining through, which prevents it from interfering with the light sensor. Plus, it looks a lot cleaner than seeing the LED glow through transparent or light-coloured plastic. Once you've finished printing all the components and assembled the PCB using those guides, the complete enclosure comes together like this. And that's the complete IR and RF hub, fully assembled and ready to go. If you've built one yourself, I'd love to hear how it works for you. Drop a comment with your thoughts, any questions, or if you've made your own version. Thanks for watching, and I'll see you in the next one. Bye for now.